The year is 1836. Deep in the archives of the Leiden Museum, a Dutch zoologist named Coenraad Jacob Temminck pores over a collection of specimens from a distant land. Among the preserved fish and shells, he finds something extraordinary. It is a sketch, hastily drawn but clear in its details. It shows a creature of impossible proportions. A crab, yet unlike any crab known to European science. Its legs are long and spindly, like the legs of a giant spider. Its body is a small, hard shield. The notes accompanying the drawing are sparse, filled with the awe and disbelief of the sailor who first saw it. They speak of a monster from the abyssal depths off the coast of Japan, a taka ashigani, or long-legged crab. This was the West's first glimpse of a creature that seemed to defy the very logic of nature. For decades, this creature remained a myth, a sailor's tall tale whispered in port towns. The drawings were filed away, dismissed by many as fantasy. How could such a delicate, spindly animal exist in the crushing pressure of the deep ocean? How could it support its own weight? The questions were many, but the answers were few. The technology to explore its habitat simply did not exist. The Japanese spider crab was a ghost, a shadow lurking in the human imagination, born from a single, dusty sketch in a European archive. Its existence was a puzzle, a biological paradox that seemed more at home in fiction than in the sober pages of a scientific journal. Then, as the 19th century progressed, more evidence began to surface. Fishermen in Japan, using deeper nets and more advanced techniques, would occasionally bring one to the surface. These were not ghosts. They were real, tangible beings of staggering size. The largest specimens stretched nearly 4 meters from the tip of one claw to the other. They were living giants, survivors from another time. Each new specimen that arrived in the museums of the world was a challenge. It was a direct question posed by nature to the scientists of the day. How am I possible? The archival records are filled with this sense of wonder and bewilderment. Today we have more than just sketches and sailors' stories. We have footage, data, and the tools of modern science. Yet the sense of wonder remains. The Japanese spider crab, Macrochaera kayamferi, still feels like something that shouldn't exist. It is a creature that tests the limits of biological engineering. Its very form challenges our understanding of the physical laws that govern life on Earth. To truly understand this magnificent animal, we must look beyond its strange appearance. We must become physicists and engineers, using mathematics and mechanics to decode the secrets hidden within its ancient design, a design first hinted at in that dusty archive over a century ago. Let us try to comprehend the sheer scale of this animal. Imagine a small car. Now imagine a crab that could almost span its width, with a leg span up to 3.8 meters. The Japanese spider crab, the largest arthropod on the planet. Its body, the carapace, only about 40 centimeters across. But its limbs define its colossal presence. When it stands, it can tower over a human lying on the ground. When it walks, it moves like an alien machine, a delicate yet immense structure navigating the seafloor. This isn't just a big crab. It's on a scale that seems wrong for an exoskeleton. That enormous size creates a physical problem. On land, it would likely collapse under its own weight. The laws of physics, the square-cube law, explain why. As an object gets bigger, volume and mass increase by a cube. Surface area and leg cross-sections increase by only a square. So larger animals end up with proportionally weaker legs. A spider crab on land would be a prisoner of gravity, legs buckling under the load. Old archival scientific notes wrestled with these impossibly high stresses. So how does it survive? First answer, its environment. The sea provides a crucial ally, buoyancy. Water's upward force counters gravity, reducing effective weight. That lets it move with a grace impossible on land. It becomes a nimble, effective navigator of the deep. It uses its liquid world to overcome gravity's limits. But buoyancy isn't everything. The crab's body is a complex machine of levers and joints, all functioning under immense pressure, hundreds of meters down. Its biomechanics are a masterclass in efficiency and strength. The shape of its shell, the material of its exoskeleton, the arrangement of its muscles. Every detail is a finely tuned solution to being gigantic. Understanding it means understanding pressure, understanding the mechanics of materials, understanding the engineering of life. The mystery isn't just that it exists, it's how it manages existence with such elegance. To truly appreciate the Japanese spider crab, we must go beyond simple observation. We need to look at it through the lens of a physicist and an engineer. We will not just show you this incredible animal, we will deconstruct it. We will explore the mathematics behind its movement, the physics that governs its life in the crushing deep, and the hidden biomechanical adaptations that make its existence possible. This is a journey into the engineering secrets of one of nature's most extreme designs. We promise to show you the calculations, the diagrams, and the principles that explain this marvel. We will begin by examining the archival materials that first introduced this creature to the world. Archival note on one side, and a modern 3D model of a crab's leg joint on the other. Old notebooks, museum specimen tags, early scientific papers. They contain the initial questions and the first attempts at answers. We will bring these historical documents to life, using them as a starting point to build our modern understanding. We will recreate the simple calculations that 19th century naturalists might have performed and then build upon them with the sophisticated tools available to us today, showing how our knowledge has evolved from pure wonder to scientific certainty. Prepare to see kinematic sketches that break down the crab's unique slow-motion gait. We will use simple equations to explain the concepts of torque and leverage. How does it generate enough force to move? How does it maintain stability on the uneven terrain of the ocean floor? We will use graphics and animations to make these complex mechanical principles clear and intuitive. This isn't just a nature documentary. It's a lesson in applied physics, with one of the world's strangest creatures as our subject. We will make the math and physics behind this animal accessible to everyone. This journey will set the stage for our deepest dive yet. We will investigate the hidden adaptations that are not immediately obvious. We will explore the secrets of its shell, the mechanics of its difficult molting process, and the sensory world it inhabits. We will explain how it manages buoyancy during its vertical migrations and how its body is designed to conserve energy in the cold, dark depths. By the end, you will not just see the Japanese spider crab as a strange and wonderful monster of the deep. You will see it as a triumph of biological engineering, a perfectly crafted solution to an extreme set of physical challenges. At the heart of the Japanese spider crab is its body, the carapace. It is a small, pear-shaped shield that seems almost insignificant compared to its sprawling limbs. In a fully grown male, this carapace might measure up to 40 centimeters wide. It is the command center, the fortress, the engine room for the entire animal. This is where all the vital organs are housed, protected from the immense pressures of the deep sea. The shape is no accident. Its rounded, slightly domed form is structurally sound, excellent at distributing the force of the water pressing down from all sides. It functions like an arch or a dome in architecture, turning external pressure into internal compressive strength. This central body is surprisingly lightweight for its size. If you were to hold just the empty carapace, you would be struck by its lack of heft. It is a marvel of material efficiency. The crab's biology has selected a design that provides maximum protection for minimum mass. Every gram of weight saved is a gram that does not need to be carried by its slender legs. Early naturalists, examining the first dried specimens, noted this in their archives. They marveled at how something so large could be constructed from such a seemingly delicate shell. The carapace is a masterpiece of optimization, honed by millions of years of evolution in an environment where weight is a constant burden. The surface of the carapace is not smooth. It is covered in nodules and spines, what biologists call tubercles. These bumps are not merely decorative. They serve several crucial functions. Firstly, they further strengthen the shell, acting like reinforced ridges that prevent buckling under pressure. Secondly, they provide excellent points for camouflage. Algae sponges, other small marine organisms, readily colonize this textured surface. The crab even actively decorates itself, picking up items from the seafloor and placing them on its back. This turns the crab from a conspicuous giant into just another lumpy, inanimate part of the seabed, hidden from predators like octopuses. Section 2, the engineering of reach, legs like levers. The most defining feature of the Japanese spider crab is, without a doubt, its legs. There are 10 of them in total, arranged in 5 pairs. The front pair has evolved into large claws, chelipeds, which can be formidable weapons. But it is the other 4 pairs, the walking legs, that truly defy belief. Each leg is a long segmented tube, tapering to a fine point. When fully extended, the longest legs can measure over 1.5 meters each. They are what give the crab its colossal 3.8 meter span. They are extraordinary biological structures, functioning as a system of levers that must be both incredibly strong and surprisingly light. Each leg is a series of hollow tubes connected by simple hinge joints. These joints are a critical piece of the biomechanical puzzle. Unlike a human knee, which can move in multiple directions, the crab's leg joints are much more restricted. They primarily bend and straighten in a single plane. This might seem like a limitation, but it is actually a design for stability and efficiency. By constraining the movement, the crab reduces the number of muscles needed to control each leg and minimizes the risk of the joint buckling in the wrong direction. The archival sketches from early zoologists often focused on these joints, trying to understand how such simple hinges could support such a massive structure. The muscles that operate these long levers are located inside the hollow exoskeleton. They are not bulky. Instead, they are long and fibrous, optimized for slow, deliberate movements rather than speed. Think of them as high-torque, low-speed engines. They pull on internal attachment points, using the principles of leverage to move the massive limbs. Because the legs are so long, even a small contraction of a muscle near the body can produce a large movement at the tip of the leg. This is an incredibly energy-efficient way to walk. The crab does not need to waste energy on fast, jerky motions. It glides across the seafloor with a slow, measured grace. The 2 front claws are different. In males, they can become particularly massive, sometimes growing even longer than the walking legs. These are not primarily for walking. They are for defense against predators, for competing with other males, and for grasping and tearing food. The mechanics here are different, focusing on crushing force rather than locomotion. The claw, or pincer, is a classic example of a third-class lever, where the muscle applies force between the pivot and the load. It is a powerful tool, the final piece in the crab's arsenal of specialized limbs, each one an engineering solution to a different problem. We began our journey with a simple question posed by a creature of impossible scale: how am I possible? Throughout our exploration, we have seen that the answer is not a single, simple trick. The Japanese spider crab is not the result of one miraculous adaptation, but the sum of countless, interconnected solutions to a host of physical challenges. It is a masterpiece of integrated design. Every feature, from the molecular to the macroscopic, plays a crucial role. Its existence is a testament to the power of evolution to navigate the rigid laws of physics and produce a being of breathtaking elegance and efficiency. The crab is a living, breathing symphony of applied mechanics, material science, fluid dynamics. We have deconstructed this giant, piece by piece, only to find that its genius lies in how these pieces work together. The square-cube law, which should have crushed it, was elegantly sidestepped by the buoyant embrace of the ocean. This single environmental factor cascaded through its entire biology, reshaping its anatomy. Its legs, freed from the burden of gravity, evolved into long, delicate levers, optimized for reach and efficiency rather than brute strength. Its exoskeleton became a lightweight composite armor, strategically reinforced to withstand pressure, not its own weight. The crab did not break the laws of physics. It mastered them, bending them to its will through a series of brilliant evolutionary bargains. The crab's locomotion, a slow and deliberate ballet, is a direct consequence of this physical reality. Metachronal gait, wide, stable stance, simple, robust hinge joints. All are components of a system designed for one primary purpose: energy conservation in a low-energy world. Its muscles, acting like efficient pulley systems, power a machine at rest as much as a machine in motion. We have seen how its very stillness is an adaptation, a posture of patience that allows it to outlast the lean times. It is a creature that has learned to manipulate not just space, but time, waiting with a deep physical wisdom that is humbling to observe. Ultimately, the Japanese spider crab is a profound lesson in biological engineering. Every aspect of its being, from the way it balances in the water column to the microscopic hairs that allow it to hear the vibrations of the deep, is an answer to a physics problem. It is a creature that forces us to look at the world with new eyes, to see the invisible forces of pressure, gravity, and buoyancy that shape all life, including our own. It is not a monster, it is a masterclass, a dramatic, beautifully lit Japanese spider crab standing tall on the seafloor, embodying all the principles discussed. Our understanding of this incredible animal has been a journey in itself, mirroring the arc of our technological and scientific progress. It began with a whisper, a sailor's tale, captured in a hasty sketch, filed away in a dusty 19th century archive. Those early naturalists, like Coenraad Jacob Temminck, could only marvel at the dried, brittle specimens that reached their museums. They were confronted with a biological paradox, armed with only calipers, scales, and the nascent principles of physics. Their notes, filled with wonder and careful measurement, laid the groundwork for everything that was to follow. They asked the right questions, even if they lacked the tools to find the answers. As technology advanced, so did our perspective. The development of deep-sea fishing nets brought more specimens to light, confirming that the creature was not a myth, but a living giant. Then came the age of underwater exploration. The grainy black and white footage from early submersibles was a revelation. For the first time, humanity could observe the crab in its natural habitat, moving with that slow alien grace. The archival divelogs from these expeditions are filled with the same sense of awe as the 19th century notebooks. But now the wonder was coupled with precious data on depth, pressure, and behavior. Today, we stand on the shoulders of these pioneers, armed with remotely operated vehicles, high-definition cameras, scanning electron microscopes, and DNA sequencers. We can analyze the crab's movements with kinematic software, model the stresses on its exoskeleton with finite element analysis, and study the piezophilic proteins that function under immense pressure. We have moved from sketching its form to decoding its genome. Yet the core of the scientific endeavor remains the same: a deep-seated curiosity about the natural world, a desire to understand how such a thing can be. The world is filled with creatures like the Japanese spider crab, organisms that challenge our understanding and reveal the hidden beauty of the physical principles that govern our universe. From the flight mechanics of a hummingbird to the material science of a spider's web, nature is the ultimate engineering textbook, and its pages are open to anyone willing to learn how to read them. Our mission on this channel is to continue turning those pages, exploring the science behind the wonders of the natural world. If this journey into the physics and biomechanics of the deep has sparked your curiosity, if it has made you look at the world in a slightly different way, then we have achieved our goal. There are countless more stories like this to tell, countless more mysteries to explore. We are already planning our next expedition, whether it's into the heart of a volcano, the canopy of the rainforest, or the microscopic world of a single drop of water. We want to take you with us to share the thrill of discovery and the satisfaction of understanding. And so, we ask for your support in this mission. If you enjoyed this deep dive into the world of the Japanese spider crab, please take a moment to like this video. It tells us that you value this kind of in-depth scientific storytelling. And more importantly, please subscribe to our channel and click the notification bell. By subscribing, you become part of our crew, ready to embark on the next journey of discovery. Thank you for joining us in the deep. We'll see you on the next expedition.